When you only have two groups, basic geometry reminds us that if we have two groups, there's a line connecting them, a one-dimensional space. If we have three groups, they might all be on one line, or they might define a plane. So if you have more than two groups, the first decision you have to make is, how many functions do we have? What space are we working within? And this leads us to a discussion of whether we're going to have what we'll call concentrated space, multiple groups but which line up on a continuum, or a diffuse space, multiple groups that fill up a multidimensional space. Then we're going to look at follow-up analyses, which is where things get interesting, because the LDF sort of says, here's a model, and here's some numbers to help describe that model, but it doesn't have a lot of significance tests. Discriminant function grew up in an area, largely in the area of taxonomy, which is identifying species from each other. And in those taxonomies, they always worked with huge sample sizes. Everything was significant. Significance tests just sort of fell out of the tradition and affect sizes. And the size of relationships became the basis for interpreting things. As LDF got pulled into the multivariate side of experimental and non-experimental work, three different traditions for follow-up analyses grew up. And we're going to go through those carefully because they are not substitutable for each other. The point that I'm going to make is that the three families of follow-ups answer different questions. And so you've got to match the type of follow-up to the question you have, the hypotheses you have. Then we'll talk about evaluating and reporting K-group LDFs and also K-group MANOVAs, and then we'll look at a bunch of examples. Like ANOVA, LDF and MANOVA can be applied to three or more groups. When we have multiple groups, there may be an advantage to using multiple discriminant or MANOVA functions to maximally discriminate among the groups. That is, we must decide whether the multiple groups line up on a single continuum, called a concentrated structure, or whether they are best described by their position in a multidimensional space, called a diffuse structure. The maximum number of dimensions for a given analysis, how many LDFs we might have, is the smaller of two numbers. It's either the number of groups minus one, or it's the number of predictor variables. The number of groups minus one is the geometrical idea. There's only one dimension in two groups. There's no more than two dimensions in three groups. There's no more than three dimensions in four groups, on and on. The number of predictor variables is sort of a factor analysis limitation. You can only have as many independent combinations of a set of variables as there are the number of variables in the set. So if you've only got two variables, there's only two weightings of those that will give you orthogonal structure. So what's the maximum number of dimensions for a given analysis? A question that I'll ask you consistently. If we've got four groups with six predictors, number of groups minus one would be 3. Number of predictors would be 6. The maximum number of dimensions is the smaller of 3 and 6. It would be 3. Make sense? So the number of groups minus 1, the number of predictors, the smaller of those is the largest function structure you might have. Something that I want you to get good at, because it is important for anticipating the difference between concentrated and diffuse structure, and also because it's important for discriminating between the bivariate and the multivariate results, is I want you to be able to look at a set of means and make a good guess whether you're going to get a concentrated or a diffuse discriminant structure. Remember, a concentrated structure means the groups line up on a single function. What that translates to is the variables all do the same thing in terms of differences among the groups. For example, look at variable 1. We got groups 1, 2, and 3. Variable 1. Does variable 1 have any difference among the groups? Is it going to help us with discrimination? Alright, now, what will it do for us? Will variable 1 tell group 1 from group 2? Will it tell group 1 from group 3?
Yeah.
Will it tell 2 from 3?
No.
Okay, that's what variable 1 does for us. It tells us 1 from 2 and 3, but doesn't tell 2 and 3 apart. So far, so good? Let's look at variable 2. Does variable 2 do anything for us? No. It's not going to be part of the function, unless it's got some cool suppressor thing, which is why we run multivariate analysis. How about variable 3? Is variable 3 going to do anything for us? Is it going to do the same thing or a different thing as variable 1? Same thing. So right now, it looks like we're going to have variable 1 and variable 3 together in a concentrated structure. It's going to put group 1 here, group 2 and 3 here, and that's what it does for us. How are we doing? Look at variable 4. Is variable 4 going to do anything for us? Now, listen to the question I ask. Is variable 4 going to group those 3 groups the same way as 1 and 3?
No.
Sure it does. 1 is different from 2 and 3. 1 is different than 2 and 3. 1 is different than 2 and 3. So 1, 3, and 4 are going to come together to give us a concentrated structure with group 1 in one place and 2 and 3 together somewhere else. Now, is the direction of contribution of variable 4 the same as the direction of contribution of 1 and 3? No, because for 1 and 3, group 1 has the low scores, 2 and 3 have the high scores. For 3, 1 has the low score, 2 and 3 has the high score. For variable 4, 1 has the high score, 2 and 3 has the low score. So the discriminant function is going to be made up of variable 1, variable 3, and variable 4. But the weighting of variable 4 is going to be negative. Because if you're in group 1, you have a low score here, a low score here, and a high score there. And so whatever weights variable 1 and variable 2 have, variable 4 is going to be backwards. Does that make sense? Does it? It's like some variables are positively correlated with the criterion, others are negatively correlated with the criterion. Same thing. Negative weight means the same thing it always does.
Do we consider it a suppressor?
No, it's just a negative correlation. In order to do a suppressor, the suppressor would be if this one popped or this one flipped when we ran the multivariate analysis and looked at the structure weight. If when we run the discriminant function, this variable has a positive structure weight, that's a suppressor. If this has a meaningful structure weight at all, it's a suppressor, because it went from bivariately nothing to multivariately contributing. That's just a good old negative regression weight. All right, let's look at here. Is variable 1 going to do anything for us? What's it going to do for us? Separates 1 from 2 and 3, right? Does variable 2, is it going to do anything for us? Now, in terms of how it groups the groups, does variable 2 do the same thing as variable 1? Yeah, it separates 1 from 2 and 3. If variable 1 has a positive weight, variable 2 will have a negative weight. How are we doing? So 1 and 2 are together on the same function with opposite weights. Variable 3 going to do anything for us? Does it group the variables the same as variables 1? I'm sorry, does it group the groups the same as variables 1 and 2? No. So this is going to build a second function. And that function is going to separate group 3 from group 1 and 2, but not from each other. How about variable 4? Does variable 4 do anything for us? Does variable 4 do the same thing as 1 and 2, or the same thing as 3 in terms of grouping groups? Same as 3. Is it going to have the same sign or the opposite sign as variable 3? Same sign. Make sense? Now, do the two functions, one that's made out of variable 1 and variable 2 with opposite signs, and a section function which is made up of variable 3 and variable 4 with the same sign, are those two functions together going to do a better job than either one by itself? This first function is not going to separate 2 from 3. The second function will, but it doesn't separate 1 from 2. So the two functions together do more than either one by itself. That's why we have multiple functions. Because if we have this space, okay, that first function is going to tell this from those, but not going to tell them apart at all. The second function is going to tell these apart from each other, but won't tell those three apart. But you put the two functions together and we can separate all the variables from each other. That's why you have a multidimensional space for multiple groups. So let me say this one more time. The first function is going to have these two variables with opposite signs. The second function is going to have these two variables with the same sign. And I really don't care if this is negative and this is positive. I don't care if these are both positive or both negative. These two have to be different from each other. These two have to be 0. These two have to be the same as each other. These two have to be 0. Yes?
We're looking at group means.
Yep.
What those are.
Yep.
And is it likely that we often going to get same numbers like that? Or?
Oh, no. I'm just trying to make it as simple as possible.
Okay.
I'm just trying to make the idea that
But they have to be equal to be...
they will be equivalent, statistically speaking.
Okay.
Yeah.
So when you said it doesn't matter, you can say that one's negative and that one's positive as long as they're different. Is there a general convention as to
No.
who choose?
No, in general, SPSS or the LDF algorithm will have the higher coded group on the right and the lower coded group on the left, but not always. That's why you've got to look at those centroids and see which group's on the positive end, which group's on the negative end, and then the structure waits to see how we align it. No, you don't. Your coding only cares to it a little, or only matters to it a little. It's not that it doesn't love us, it's that it's independent. All right, let's look here. Little bit of variability, a little bit of slop, but still pretty clear picture. Is variable 1 going to do anything for us? Not very damn much. Is variable 2 going to do much for us? Variable 3? Yeah. All right. Variable 4. Is what variable 2 and what variable 3 and variable 4 do similar in terms of how the groups are grouped? Yeah. Okay. So they're going to come together on a single concentrated structure. Are the signs going to be the same or different? Same. How are you doing? Okay. Is variable 1 going to do anything for us? Is variable 2 going to do anything for us? Do variable 1 and variable 2 do the same thing in terms of grouping groups? So we've got two functions right off the bat. Is variable 3 going to do anything for us? Yeah. Is it like variable 1 or variable 2 in terms of grouping groups? Variable 1. Is it going to have the same or a different sign than variable 1 on that function? Same. Does variable 4 do anything for us? We're done. We got a diffuse structure with 1 and 3 on one function, both with the same weight, same sign weight. Variable 2 makes up function 2. Does the notation make sense? These two contribute to function 1 with the same sign. This contributes to function 2. A 0 means I'm not part of that function.
I'm just confused. Really how 5 are supposed to be?
You're going to have significance tests for real. What I'm trying to do is give you really clear patterns and have you recognize those really clear patterns. All of this will go to shit with real data. Okay? But the significance tests will help.
So basically later on we'll compare the different LDS to see which ones discriminate between the groups the best? Or?
Yes. You might do that. What you're going to start out doing is saying, okay, what does each variable do for me by itself? What does the function do? Are there any multivariate surprises? All right, does variable 1 do anything for us? Does variable 2 do anything for us? Same or different than variable 1? Same. Separates 1 and 2 from 3. Same sign or opposite sign does variable 1? Same sign. Does variable 3 do anything for us? Same or different from 1 and 2? Different. Does variable 4 do anything for us? Good. Now be careful. In terms of grouping the groups, does variable 4 do the same thing as 1 and 2 or the same as 3? 1 and 2. Does variable 4 have the same sign or the opposite sign as 1 and 2 on the function they all belong with? How are we doing? That's all there is to it. Look for groups, look for sign. And I will tell you that if you do a careful job of the order in which you put these variables into the discriminant function, because you can control the order that you put them in, when you get that table of means out, and you can sit there and say, well, you can see that these variables all sort this way and these variables sort that way, but this one's got a negative relationship, especially when you can do that live in front of a client or a collaborator. Oh, they're like puppy dogs. Okay? One of the clearest indications that somebody knows how a multivariate model works is to be able to look at the bivariate results and anticipate what's going to come out of the big fancy model. That's how you convince people, whether it's your advisor, your teacher, or someone else that you care about, that you know what the hell's going on. Being able to look at that bivariate structure, anticipate the multivariate structure is one. 2, what you brought up, being able to recognize the difference between the multivariate structure we anticipated from the bivariate structure and the surprises. The collinearity effects where things don't have a unique contribution because they're highly correlated to somebody else. For example, these two variables are probably pretty highly correlated with each other based on their mean structure across groups, right? So they're going to be collinear. So in terms of the discriminant function standardized weights, these might not have a big unique contribution to each other. Even though, because they're the same as each other, they're going to define that function. You with me? That's the difference between unique contribution and defining the function. That's why we look at both the structure weights to define the function and the beta weights to talk about unique contribution. All right, we're not going to do the last one.
Cal.
Yes?
So if you had, like on variable 1, let's say your scores were all really, really close together.
Uh-huh.
Like 19, 20, 21. So that does nothing for you. But then you have another variable where it's 10, 20, and 30. So I mean, they're all, it's still 0 just because of...
No, this one's going to do what it does. Only this one's sweet. It separates all 3 groups from each other.
So you could have 3 functions.
No, this is one function.
But you could have variables that either do nothing, separate, put 2 groups together and 1 apart, and then you could also have a function where all 3 are separated.
It's unlikely, and usually what it'll do is it'll figure out which of these this is closest to, which of these this is closest to and wedge them all together. That's why there often are surprises between the bivariate pattern and the multivariate pattern, because the most effective multivariate pattern might not use each of the pieces.
So when you're using the diffuse, though, you generally just have 2?
Basically, you hope for 2, because 3 is a real booger to display and describe. And so if you're working with 30 groups and you have a 6-dimensional structure, it's not what you sat up early thinking about and hoping for. But you dig in and go on. But yeah, you're right. And we will usually constrain you to working with 2 function models for homework. Because, again, if it's not your data and you're not deeply interested in the variables, working with multidimensional structures gets ugly. But it can be what's really important. Because it might be that 3rd or that 4th function that breaks off that one group that you really care about. Because why do you care about that group? Because they're hard to tell from the others. So it might not be the first couple of simple functions that do that last thing you really didn't want to do. Because it is ugly out there, and sometimes the model has to be ugly to capture out there. Great questions. So we've talked about guessing how many functions there might be. We can guess the maximum number here. It's the smaller of the number of groups minus 1 or the number of predictors. We can anticipate it by looking at the means patterns for the variables. But what we really do before it's all over is we have a significance test. Each LDF or MANOVA variate is tested as to whether it contributes to the model using the chi-square or an F-test. If it's an LDF, you'll see a chi-square test. If it's a MANOVA, you'll see an F-test. So it says, all right, is the first function any good? There's an F-test or a chi-square test for it. Then, is the second function any good? Until it has exhausted the number of possible functions, testing for each, whether or not we care. The first variate, the first function, will always account for the most between group variation. It will always have the largest chi-square, it will always have the largest F, it will always have the highest canonical. Subsequent LDFs are orthogonal, which means they're at right angles to each other in space, or from our perspective, they provide independent information and account for successively less between group variation. By having that information orthogonal to each other, we get the most information out of the combination possible. So what each one tells us, none of the earlier ones did. If there is a single variate, the model is said to be concentrated. If there are two or more, it's said to be diffuse. And the distinction between a concentrated and a diffuse structure is considered the fundamental multivariate question. That's the first question we have. Do these people line up, or do they spread out in space? Any other question you want to ask is dependent upon the right answer to that first question.